Okay students, so in this lecture we are going to try to look at some algorithms to find least square solution. So in the last class, please recall that we defined the pseudo inverse of a matrix and we said that x star equal to the pseudo inverse of a matrix times b. By the way, pseudo inverse is written with a plus usually as a superscript of the matrix A. Right? We said pseudo inverse can be defined for any matrix. All you need to do is take the thin SPD of A. So U sigma V transpose, where sigma is a diagonal square matrix consisting of the singular values of the non-zero singular values of the matrix A, and the pseudo inverse is defined as V sigma inverse U transpose. Okay. In the case when A is skinny full rank, the pseudo inverse computed to also A transpose A inverse A transpose B, right? And we had a similar slightly different expression when A is fat full rank. Okay, so we said that x star equal to A pseudo inverse B solves the least squares problem, i.e. it minimizes norm of Ax minus B whole square, right, for any x, right? And it also gives a min norm solution if it exists, right? It gives a min norm solution, that is minimize norm of x among all x such that Ax equal to B. Okay. So unlike the least square solution which always exists, remember that the min norm solution may not exist because in fact there may not be any x that satisfies Ax equal to B. Okay, so there may be nothing to minimize over here, right? So min norm solution may not even exist, but least square solution always exists. There is always an x that minimizes this, right? That minimum value could also be 0, it could be non-zero. But there is always an x that minimizes this. There could be many x that minimize this depending on whether A is full column rank or not. If A is full column rank, then there is a unique minimizer for this problem. Okay, all this was discussed in the last class, right? So from here we'll just focus specifically on the case when A is skinny full rank. Okay, and in that case we know that the pseudo inverse is A transpose A inverse A transpose B. Okay, this is the minimizer for the least squares objective, right? And this is the least squares objective. Okay, so now what we are going to do in this lecture is we're going to spend some time, little bit of time thinking about how to actually go about computing this quantity. Okay, considering the importance of this problem and the wide variety of applications it has, it makes sense to think and try to optimize about what sort of procedure to use to actually compute this. Okay, so let's just take a quick reminder about the sizes here, right? So A is an m cross n matrix and A is skinny, right? So m is bigger than n. We'll assume that m is bigger than n. Okay, and the columns of A are all linearly independent. Okay, so just quickly jot down the sizes here. A transpose A is going to be an n cross n matrix, right? A transpose is going to be an n cross m matrix and B here is an m cross 1 matrix. Okay, now of course what you're getting x here is an n cross 1 matrix. Okay, fine. So now let us just try to do a naive kind of like just try to take the inverse and try to apply the naive method to actually compute this and see how many operations that will need. Okay, so before we do that, I just want to very quickly talk about how do we measure algorithms in having to do with matrices, right? So any algorithm usually will take as an input, let's say, some matrices. So in this case, the algorithm, the least squares algorithm, has to take as input the matrix A and the vector B, right? These two have to be given to the algorithm and the output of the algorithm has to be x star, the least square solution that minimizes Ax minus B whole square. Okay, so generally any algorithm, in linear algebra would take matrices. So here they're taking two matrices. One of them happens to be just a vector and it outputs another matrix, in this case just a vector. Okay, for example, an SVD algorithm is supposed to take a matrix A as an input and output three matrices, that's U, sigma and V, right, such that U sigma V transpose is equal to A. Okay, so SVD algorithm takes a matrix as an input and outputs three matrices, right? Similarly, as a decomposition, let's say QR algorithm will take a matrix A as an input and generate Q and R as output, okay, such that A is equal to QR. So here two matrices are generated as outputs. So Q is orthogonal and R is upper triangle. Okay, so these matrix algorithms take matrices as input and output some important feature of the matrix, right? It could be decomposition, it could be some other property like let us say the inverse of the matrix, or it could be like the determinant of the matrix, whatever, right? Generally, as a thumb rule, most interesting matrix algorithms, okay, like the SVD, okay, or the QR, okay, most matrix algorithms take order of larger dimension cross smaller dimension whole square to compute. Okay, so this is just a thumb rule. It's not true universally. I mean, for example, obviously if you want to find the trace of a matrix, that's just going to be order n, right? Order of the smaller dimension, right? I mean, of course, trace for a square matrix, so it's just order of the dimension. So it's not like a universal thing, but it's just something to remember. Similarly, multiplying a matrix, let's say we're multiplying an m cross n matrix A with an n cross 1 vector x, right? That takes order mn operations, as we discussed before. And operations for us are measured in terms of floating point operations, right? So we're going to look at flops. It takes order mn operations. It doesn't follow in this mnemonic, but I'm saying the interesting or the more advanced algorithms like SVD, QR, even so as we're going to see, even least squares roughly take this many operations: order larger dimension cross smaller dimension square. So in our case, it's going to be order mn square. Remember, for us the size is m cross n. So matrices are of size m cross n, where m is bigger than n. So m is the larger dimension, the number of rows, and n is the smaller dimension, that's the number of columns, right? So we are going to see this order mn square pop up in most of our discussions here, right? First, that's the first thing. Second, the important thing to also note here is, even though the order is the same, it doesn't mean that different algorithms having the same order will take the same time to compute. Okay, for example, both SVD and QR roughly will have this order mn square, floating point operations, but SVD in practice will run much slower than QR. Okay, the reason for this is that there is also a proportionality constant involved, right? So when we say order mn square, we roughly mean some constant times mn square, right? This is the upper bound on the number of operations required, some constant times mn square. So this constant value could be very, very large for some algorithms and very small for some other algorithms, right? So when we say order mn square, we only mean that if m and n become very, very close to infinity, then they roughly take the same number of operations, right? But the constant factor will play a role in practice, right? So in general, over SVD and QR, if you could get your task done with just QR, you would prefer QR, okay? Because QR will run the same order mn square, but with a smaller constant factor, it will run faster. Okay, so that's the first thing which you judge an algorithm by. You judge an algorithm by how many flops it takes to compute, right? And the number of flops both has an order component and a constant factor component, right? The second thing you judge algorithm by is its stability. Okay, stability basically is the idea that we talked about when we did the lecture on matrix norms, right? So whenever in practice, when you're thinking of a matrix as being an input to an algorithm, we cannot really assume that this matrix is given exactly, right? So there will be some errors, either due to finite precision or due to maybe some noise. Maybe this matrix A is actually measured, in which case there is natural to assume some measurement noise here, right? So the entries that go in here are not the true value of A, but the true values of A with some perturbation, some noise, right? Then the question is, how does noise flow through the system, right? So does this algorithm amplify the noise that's inherent in the system, or does it not amplify it? Okay, so that's basically what is called the stability of the algorithm, right? The lesser the algorithm amplifies the inherent perturbations in the input, the more stable it is. Okay, an ideally stable algorithm is one that will not amplify the input error at all. Whatever the input error is, it will let it go through. Okay, so that's a very stable algorithm. For example, if you're talking about an algorithm to compute an input vector x with an orthogonal matrix Q, okay, so the output is just qx. So orthogonal multiplication is very, very stable, right? Because even if there is a perturbation in the input, that just gets multiplied with, let's say there is a delta x perturbation at the input that gets multiplied as q delta x at the output, and the norm of q delta x is the same as the norm of delta x because q is orthogonal. We discussed this in the first segment, right? Orthogonal matrices don't amplify errors. Okay, fine. So stable algorithms are desirable. Usually stable algorithms are desirable, but often, you know, there is going to be inherent instability in the system. For example, any algorithm that has to deal with inverses. Okay, so basically you have an input A to the algorithm and the output has something to do with inverse. Maybe the algorithm is actually computing A inverse, or maybe it's computing some variant of A inverse, maybe like pseudo inverse, right? Something else, right? In this case, the algorithm will naturally be as stable as the condition number of A allows, right? So remember we discussed in the lecture on matrix norms, the condition number of a matrix, written kappa of the matrix A is the ratio of the largest singular value of A to the smallest singular value of A, right? So in general, any errors will get amplified by this much, the condition number for sure. Okay, so basically here also, whenever you have an algorithm that takes a matrix A as an input, we would expect, and this algorithm is doing inverse or some such operation, we would expect that the stability of the algorithm will depend on the condition number of A. Okay, so if the condition number of A is large, meaning the matrix is poorly conditioned, recall that if the condition number is large, then the smallest eigenvalue is close to 0, meaning the matrix is close to being rank deficient, okay, close to being a low rank matrix. Then in that case, condition number will be very large. So basically what I'm trying to say is that if the condition number is large, then you expect that the algorithm will be unstable. Okay, so the stability of the algorithm will scale with respect to the condition number, but once again, just like the order here, the scaling may be very, very different. Okay, so some algorithms may actually amplify it even beyond the condition number of A. Okay, so the errors may get amplified even beyond the condition number of A. Okay, so this is just roughly speaking what I'm trying to say. I mean, we didn't do any rigorous analysis or anything here, but it's trying to say that these are two issues which we need to analyze. There are two aspects on which we need to analyze algorithms on. Okay, fine. So with that in mind, let us discuss the most naive and simple algorithm to find the least square solution, which is to directly find this quantity. Okay, so let's try to do that. Okay, so let's try to compute A transpose A inverse A transpose B. Okay, the input to the algorithm is A, an M cross N matrix, and B, an M cross 1 vector. Okay. So let us try to see how many computations are required to compute A transpose A. Recall that A transpose A is an N cross N vector. The number of computations required to find A transpose A is going to be mn square, because you remember A transpose is going to be a matrix that is very fat, considering that A is very skinny, right? So here is going to be N cross M. So this dimension is N, this dimension is M. Okay, here again this dimension is M, and this dimension is N. So when you compute the inner product here with this, right, so the inner product computation takes order M, and you have to do this overall for each of these N rows with each of these N columns, so N square times, so that's order Mn square, right? So computing A transpose A, the gram matrix, takes Mn square operations, okay, Mn square flops. Okay, fine. So that's Mn square. Now I compute A transpose A, the gram matrix, then I have to invert it. Right, so A transpose A, remember, is an N cross N matrix. To invert the N cross N matrix, I'll take order N cube operations. Okay, I haven't discussed how to do this exactly, but you know, one way you can think of doing it, taking the inverse of a square matrix, is find its spectral decomposition. Right, once again, spectral decomposition will be order N cube. If you follow this mnemonic, larger dimension into smaller dimension square, finding the spectral decomposition of a square matrix will be order N cube. Okay, fine. So it will be roughly order N cube. So taking the inverse will be order N cube, finding the gram matrix will be order N square. So let me just roughly write down, you know, so order Mn square plus order N cube. You know, so this is very weird, but you understand what I mean here, right? So this is so far computing this. Okay, right. Now taking B, multiplying it with A transpose, this quantity over here, finding this product, right, will take you how much? So remember, B is an M cross 1 vector and A transpose is very similar to this, right? So A transpose times B. right? So that's going to take you order mn. Okay, get back to me if you have any questions on this, right? Okay, let's order mn, right? So that gives you this vector, which is going to be an n cross 1 vector. Now this is an n cross n matrix multiplying with an n cross 1 vector. That's again going to take you order n square to compute. Okay, this is going to be the total number of roughly the computations required, and as you can see, m is bigger than n for us, so you can safely say that this is what dominates, so to speak, right? So once again, you see, just with this naive operation, computing the least square solution is order mn square. Once again, as you know, the thumb rule here suggests, once again it falls in that category, right? It takes order mn square operations. Okay, fine. But there are two main issues with this, right? One issue is that you actually need to find the inverse of this matrix, right? And for that you will likely need to store the inverse somewhere, right? So that's order n square space complexity for sure, meaning that much memory you need. And typically in modern day scenarios, m and n will be very large. In fact, we will see later that n could actually be in the order of millions potentially, right? You may be interested in solving problems like that. So this is pretty huge. I mean, you need to worry about this a bit, right? Then apart from that, the other main issue here is with stability. So we analyzed this algorithm so far on only one aspect, that is the computations and its order mn square, right? The constant in front of this also could be large depending on what algorithm you are using to find the inverse, right? To find the inverse, if you are using like the spectral decomposition, then it's actually going to be large. But if you use something else like Koleski decomposition or something, then the constant will be a bit smaller. Okay, fine. But the bigger issue is with stability of this algorithm. So what happens here is you want to invert this matrix, correct? A transpose A. So to invert A transpose A roughly, you can expect the stability to scale proportional to the condition number of A transpose A, right? Roughly the condition number of A transpose A. What is the condition number of A transpose A? So the condition number of A transpose A will be like, you know, the largest singular value of A transpose A divided by the smallest singular value of A transpose A. The singular value of A transpose A is actually going to be the square of the singular value of A, correct? Sigma means square A. Okay, so this the singular values of A transpose A are squares of singular values of A. Okay, so this is actually the condition number of A whole square. Okay, so you can see what has happened here is that the stability scales not with the condition number of A but with the condition number of A square. Okay, so if your A matrix itself is poorly conditioned, so let us say the condition number is 10, right? You actually get, by squaring it, condition number of 100. So it's effectively that you are working with an even more poorly conditioned matrix. Okay, so there is an even higher chance of the errors getting amplified. Okay, so this is not a very ideal scenario to be in as far as stability is concerned. So these two are the main issues with this. In addition to this, also some might say that the proportionality constant here could be very large. Okay, so these are the issues with the naive approach to finding the least square solution. So in the next portion of this lecture, we're going to discuss the popular techniques to mitigate this issue.